If you want to understand how a nuclear bomb works, you don't need a physics degree. You just need to picture a massive domino setup, where knocking over one single piece triggers a wave of falling blocks. This power comes from the microscopic behavior of atoms, which follows this same simple logic at an invisible scale. Before we understood the rules of that atomic game, the source of this energy was a heavy, inert black rock pulled from the Earth. It was called pitchblende. So how did scientists figure out how to take a quiet, natural rock and turn it into a weapon capable of erasing an entire city? For decades, researchers knew there was enormous energy locked inside the atoms of this rock, but they faced a roadblock. They couldn't crack the atoms open. Whenever they tried to shoot particles at a uranium atom, the atom's natural defenses would forcefully repel them away. The breakthrough came when researchers discovered a tiny particle called a neutron. Because a neutron carries no electrical charge, it acts like a microscopic ghost bullet. It can slip right past the atom's defenses without being pushed away. Finding this ghost bullet meant scientists could finally bypass the atom's resistance and reach the concentrated energy inside. At the microscopic level, when we fire a tiny neutron into a heavy uranium atom, the impact is too much to hold together. It violently splits in half, releasing pure energy. As it breaks, it spits out 3 brand new neutrons, launching them outward. That single tiny impact has just generated 3 new bullets. The stage is now set for unstoppable growth. These 3 newly fired neutrons act as triggers, striking neighboring uranium atoms. When they split, each releases 3 more neutrons, creating 9 new triggers. The math escalates instantly. 9 trigger 27. 27 becomes 81. Rapidly growing into a massive, uncontrolled web. Because atoms are unimaginably tiny, this doesn't take minutes or seconds. This web of billions of splits happens in a fraction of a millisecond. That instantaneous multiplication, billions of microscopic energy bursts happening all at exactly the same time, is the physical definition of a nuclear explosion. This raises an obvious question. If natural uranium atoms spit out these trigger bullets, why doesn't the pitchblende rock just explode while sitting untouched inside the Earth? It helps to think about how a firecracker works. If you pour loose gunpowder on the sidewalk and light a match, it doesn't pop. It just quietly fizzles and burns away into smoke. To get a massive bang, that powder has to be tightly wrapped and trapped inside a dense casing. You have to lock it in so the energy has nowhere to escape. Natural uranium in the ground is like loose gunpowder. The atoms are scattered too far apart. The ghost bullets usually glide off into empty space, missing the next uranium target. The real historical challenge wasn't just splitting the atom. It was engineering a way to pack the atoms so closely together that a hit was guaranteed. Scientists solved this by designing what we see in this cross-section. They took a core of pure uranium and surrounded it with standard conventional explosives. When those outer blocks detonate, the force of the blast pushes entirely inward, squeezing that small uranium core. This extreme pressure shoves the uranium atoms so tightly together that there is no empty space left. The second that first atom splits, the chain reaction is instantly guaranteed. Engineering this perfectly inward squeeze required incredible precision. That is why the first weapons had such massive casings. They needed all that bulk to house the explosives crushing down on the core. A moment of wonder. By learning to pack these microscopic dominoes so tightly, humanity forces the universe to release its deepest energy.
I hope you enjoyed this deep dive. If you want to keep exploring history with us, make sure to subscribe to Ask the Timeline and turn on notifications. Every like helps this channel grow